A nanometer is defined as 1/billionth of a meter. 1 times 10 to the minus 9 meters.
On the cutting edge of material science, Dr. Jeffrey Brinker is developing nanoscale materials to do amazing things, such as curing cancer.
So when it comes in contact, it will interact with that cancer cell and go into it, and then we have the Trojan horse effect occur.
What they did for my spirit and my soul as a person, and what they gave to me, was far more than what I could give to the people there.
Sharing how the simplest things made a huge difference, UNM nursing student Antoinette Russell talks about her experiences volunteering in a medical clinic in Kenya. How do we know a meteorite is from Mars? In this month's viewer question, we discover something truly out of this world, a newly acquired Martian meteorite. From nano to the cosmos, welcome to Connect. Each month, we connect audiences to the great people and inspired thinking found at the University of New Mexico. Connect is next. I'm here with Jeffrey Brinker, distinguished professor at UNM. You are on the forefront, basically, of a revolution in medicine. We're talking about examples of nanoparticles that can actually destroy cancer cells.
The nanoparticles that we make, which are, get this 100th or 1,000th times smaller than a cancer cell, one particle loaded with a particular cocktail of drugs can kill one cancer cell. So it's an amazingly efficient ability to kill cancer with these particles. And the whole concept is that we want to deliver drugs directly to cancer cells and nowhere else in your body. I think everybody is familiar with chemotherapy, where you just inject pure drug into your veins and the drug goes everywhere. And it kills cells that tend to reproduce very fast, like cancer cells, but also your hair, right? So everyone goes bald, this sort of thing. So what we're trying to do is put all the drugs in a tiny particle that can go directly to the cancer cell of interest and kill that cancer cell. And the center of that particle is essentially a sponge created on the nano scale, okay? And that sponge, if you put it into a beaker with your drugs, it will suck up the drugs into the sponge. And this sponge, these particles that we make, just if you can think about this, so if I were able to unfold the nanostructure within them, I would get a carpet with 1 gram of powder. I would get a carpet 10 meters wide and over 100 meters long with 1 gram of material. So this internal surface area sucks up and absorbs all these drugs. So that's sort of on the inside. But on the outside, we disguise the particle to allow it to not be recognized as a foreign invader by your body. And we put particular types of molecules on it that are recognized by the cancer cell surface.
And sort of accepted by it.
Right. And so we can direct these particles to interact with the cancer cell surface. And through this interaction, they get taken up actually into the cancer cell where they release their cargo. So it's kind of a Trojan horse from the standpoint on the outside, it looks friendly to the cancer cell, but once inside the cancer cell, we have a surprise.
The cancer cell doesn't know what it's in for. Tell us about nanoparticles.
Why do we use nanoparticles? Again, they're very small relative to the size of the cancer. And that smallness is really important for several reasons. First of all, the small particles have to circulate in your body, okay? So you inject it into your body. If the particle is too large, it might be viewed by your immune system maybe as a bacterium or something, and it would get cleared out of your body. And if it's really too small, it might go through your renal system and go out in your urine. So there's a particular size particle that most efficiently can enter the cancer cell, because without getting the drug inside, again, you don't kill it, okay? And then there's also penetrating a tumor, so that you all familiar with the primary tumors of a cancer. So you want this particle small enough that it can work its way into the tumor and access all of the cells within the tumor. And then another really serious problem of cancer is not just the primary tumor, it's metastasis. So what we want are these small particles that can penetrate everywhere and hopefully find and seek out and destroy these metastatic cancers.
It really is minuscule beyond belief.
I can't just point to them because they're so small. We have to look at them with very powerful microscopes. But a nanometer is defined as 1/billionth of a meter. Wow. 1 times 10 to the minus 9 meters. And that's just, you can't even think about things on that scale. These particles that we're using are 100 or 1,000 times smaller than a typical cell in your body. And so, and they're of the size of molecules, right? So what we want to do is we want to have the interior of this particle, this sponge, if you will, have a pore size that just the right size to accommodate a drug molecule.
There must be some challenges with the types of equipment that you have to use to even study this.
There are two aspects of this. One, the equipment that we need to look at these particles is very expensive because we have to use what's called electron microscopy. But I can make these particles with very simple techniques. And so the one major way that we make the particles that we're using, these nano sponges, if you will, is to do something just like, I think everybody's familiar with a vaporizer, right? So you can plug it in and it creates little liquid droplets, okay? And so what we do is we make liquid droplets, and within those liquid droplets we put particular chemicals that when the droplet evaporates, the chemicals are programmed, essentially pre-programmed to form this nanostructured material. So it's simple. It's called self-assembly. So this is fantastic. Like my graduate students, right? That you walk into the lab and what are they doing? They're sitting around, oh, we're doing self-assembly, right? So the particles assemble themselves.
Wow.
So we developed this extremely robust way to have the particle nanostructure form by itself. So that's very easy for us, that part. And then once we form this sponge, we do something else that's pretty simple. We put on the outside of this sponge what's called a lipid bilayer. So every cell in your body is covered by this lipid bilayer. It's a very thin membrane. And so we put that over top of this sponge. So we load the sponge with our drugs and we put this membrane over it to keep the drugs in. And then on the surface of the membrane, we put molecules that recognize a particular cancer. So the particle is kind of stealth-like. We can, on the outside, it doesn't get recognized by your body's immune system, but it has a few of these, what we call targeting ligands, that will recognize the cancer cell. So when it comes in contact, it will interact with that cancer cell and then go into it. And then we have the Trojan horse effect occur.
How do you get them to do what you want them to do once they're in there?
And we do that by putting molecules on the surface of this particle. And we identify these molecules by kind of a fishing expedition kind of thing. So we make a library of a whole bunch of very small, what are called peptides. These are just very small amino acids combined together, like a very small protein. So you can imagine if we had a huge library of all kinds of random peptides like this, and we sort of dip them into the solution with our cells, right? Mm-hmm. And we sort of see which ones stick and which ones don't. And then, so we identify peptides that only stick to the cancer that we're interested in. And so we use that peptide that we identify, we put it on the surface of our particle. Wow. And it will go in and, it doesn't get directed toward the cancer, but if it encounters the cancer, it will start to bind to it. And this binding leads it to get internalized or taken into the cancer cell. So we have two really expert women in our lab, Carly Ashley and Katie Epler, who are experts at identifying these ligands. And it's a process that you go through, but it's very robust process. And that's how we kind of train the particles to sort of do what we want them to do.
How far away are we now from, say, the human clinical trials with this research?
The research that we're doing now, a very important part is to take it into clinical trials and ultimately humans, of course. And so what we have is we have a grant that's funded through the National Cancer Institute. They have an alliance for nanotechnology and cancer. So I've teamed up, I'm a sort of a nanomaterial scientist, but I teamed up with Cheryl Willman, who directs the UNM Cancer Center. And so her interests are, of course, are combating cancer in human patients. In particular, what's called acute lymphoblastic leukemia, which is it's a childhood leukemia, and one that can have a very low outcome. And so we've teamed up to make particles that will be useful to treat this acute lymphoblastic leukemia called, well, they refer to it as ALL. So we put these molecules on the outside of our particle that recognize these ALL cells and can enter them and kill them. So in terms of how quickly can we get this into human trials, there's a progression. First, you have to show that you can kill cancer in a petri dish, okay?
Start there.
And then you have to show that you can kill cancer in a living organism. In a mouse model would be typical. And then if you can show that, then you might go to a primate, and then finally, into a human trial. The shortest would be sort of a 5-year period. That would be a very rapid, taking something out of the lab, getting it into a human clinical trial. So the FDA would have to approve this. So there are two critical things. First of all, it can't do you any harm, right? It doesn't mean that it has to really cure you, but if it has any kind of toxicity, that's a huge problem. So we have to prove that these are very, very safe. And then we have to prove that they have some benefit, right? So they help you to some extent.
What other applications and nanostructured materials can you imagine going forward?
Nanoparticles are being explored, throughout the world for other types of application. For sustainability, for us to, have a sustainable environment, we really need to focus back on solar energy. And so these particles can also be used to convert solar energy into electrical energy, right? So this is they can be used in, for example, photovoltaics.
Sure.
They can also be used to help to convert chemicals from one type to another. So you do this all the time in your car. You have a catalyst that will convert CO that's created by your engine into CO2, okay? So very small, you have a catalytic converter in your car probably. And that has nanoparticles of different metals in that case. So these are used as catalysts.
What inspires you to do this?
This porous sponge that I had described to you, I made this back in 1999. We had a paper in a famous journal called Nature that described our ability to make these sponges, okay? And I had at that time the idea that these might be useful if we could load them with drugs and use them for drug delivery. You can't just load a particle with drug without kind of sealing it inside. So it was only more recently I was thinking about these membranes that I was mentioning. So we put a cell membrane over the outside. So we were interested in understanding how do cell membranes work, and one way to study them is to support them on something and study them with a number of different physical techniques. And so I was thinking, wow, we're making cell membranes, we're also making these porous materials. Could I put the cell membrane on the outside to seal the cargo in? And that was sort of the inspiration for making this particle that we actually call a protocell.
What's the next breakthrough?
We feel that pretty soon there'll be personalized medicine, right? So now, the human genome has been sequenced. So I'm thinking, in the future, you're going to have on your driver's license your genome. And there might be certain types of medicines that are just perfect for you. So personalized medicine, right? And in these particles, like I said, they're very versatile. So we feel that we could put any combination of these drugs and make them personalized for you or someone else. And so this is, I think, one of the future goals. And of course you can build more, there's a lot of information you can build into even a nanoparticle. So they might be able to you might have a GPS system in them to see, where are they in your body, this sort of thing. So all these kinds of ideas I think are not too crazy.
What are the downsides to nanoparticles and some of the things we've been talking about?
If you build a car, I can go in and inspect every little part of the car, no problem. And so now you have this particle that you can't see. And you just have a beaker of it, and there's millions and millions of these particles in there. And how do you assure yourself that you've got what you think you have? And how do you prove it to the FDA? So you have to develop techniques that'll assure you, or a way to kind of judge what you have. That's a tricky part of this process. And then of course, cancer itself, people have the idea that cancer is a thing, but cancer can take multiple forms. Even the same type of cancer can have different subpopulations, and whether you can kill subpopulation A, but maybe you don't touch the other one. And so to really ablate cancer or destroy it, you have to kill all of the cancer cells, and that is a very tough problem.
Fascinating stuff. Thank you so much for joining us today to talk about this. I'm joined by Antoinette Russell, a level 4 nursing student at the UNM College of Nursing. Now, Antoinette, you recently took a trip to a very remote village in Africa with the group as a Helping Hands volunteer. What impacted you the most about this experience?
When we went to the district hospital one of the days, we went to the pediatric ward, and there were 2 giant rooms, and one room had tons of kids and their family members in it, and the other room was completely empty, and there was like the nurses station with a couple nurses there. And so my friend and I pulled out our cameras and we're like, let's take a picture of this to take back to the College of Nursing so students can see what the hospital's like. And after my friend took the picture, I kind of looked into the back and I saw these bundle of blankets, and I was like, I think there's a kid in here. I think there's a baby in here. So we walked back there and we see like this little baby, and he was probably age-wise 2 years old, but he looked like he was just a few months old because he was so small, and he was panting at the mouth, and he was hooked up to all kinds of IVs, and we were looking at the the medications, and it was for HIV/AIDS, and kind of just broke us to see him by himself back there with nobody around him, and we wanted to hold him so much, but we couldn't. And I asked a translator that was with us, because I was getting teary-eyed. I'm like, does this make you sad? And he was just saying, I've seen a lot of sad things.
And what do you think that experience with that HIV/AIDS baby says about the whole situation in Africa?
That they don't have the medical care there that we are so lucky to experience here. Over there, the medical staff, nurses and doctors, they're only in charge of the medical needs of the patient, but the families are responsible for all the other needs: food, washing, clothing. So if someone doesn't have family, and if they're fortunate enough to be able to afford the medical care, they're not going to be able to get the other basic needs.
By the looks of the pictures that you brought back, you spent a good amount of time with these kids.
We did.
That was, that had to have such an effect on you, those children.
It was really overwhelming to be around them so much. Every day we would walk to and from the clinic, 3.5 miles, and we would always have these kids just running up to us the whole way that we were there, and they would just grab onto our hands and walk with us for miles.
Describe some of the care that you gave the kids.
And it was a lot of like child checks. We checked their lungs, heart, ask them, how are you feeling, what's bothering you? And a lot of the kids, they have headaches, and it's because they don't get water. I would ask them, how much water are you drinking a day? They're like, a cup with dinner. And it's like, okay, in a full day you're drinking 1 cup of water, and you need to be drinking 2 liters of water. We saw a lot of kids with like fungal infections on their heads, is because they don't have soap. We saw a lot of kids with teeth decay because they don't have a toothbrush and toothpaste. And so we were able to give them soap, toothbrush, toothpaste, like multivitamins. And so it was those very simple little things that
things
they needed.
we take for granted.
Exactly, things we could go down to the store and get.
Did everyone in OU Geese, young and old, receive some kind of medical attention in the short time that your group was there?
Yes. So we saw about 2,500 patients in the span of the 5.5 days, ranging from all ages, and we tried to give something to everybody. By the last day, we were running out. And a lot of the people there, they just wanted somebody to talk to about what was happening with them, whether or not they needed something. We had one elderly lady who came almost every day just to talk. And we were like, we want to talk to you, but we have a lot of patients to see.
She needed the social
Yeah,
interaction.
so she would just come and sit down and start talking. And we were like, okay, you know, they just wanted that sometimes.
So tell me how Helping Hands, how that particular village came to get those medical services.
The women of the Wawati, which is the tribe there in Oyugis, they were tired of seeing their husbands and their children dying from AIDS. And so they reached out to Project Helping Hands to see if they could get medical services down there. That's when Project Helping Hands went there.
Were there any sort of taboos that you had to be aware of?
A lot of the things that were taboo there were centered around like sex. You know, we couldn't be open about it with them, or like asking them, you know, they wouldn't be open with you about it. So you kind of have to weasel your way into finding out if they needed condoms or, you know, pads for the girls. And so whenever I was, you know, with a patient who was, you know, that I felt was probably sexually active or whatnot, I would kind of ask at the end, like, do you need condoms? And they're like, yes. You know, like they didn't want to outright tell me it. You know, it's there, and they know that it's there, and it could be a problem with the spread of HIV, but they don't want to talk about it in the open way that we kind of communicate with our patients in American hospitals.
Sure. How did they respond to your medical care?
They were 100% open to our medical care and us, our presence being there, and it was amazing. They were so thankful for any little thing that we were able to do for them, whether it was giving them ibuprofen or Tylenol or multivitamins. There were some people there that we were able to give them the money that they needed to get procedures done at the district hospital, or their medications from the district hospital.
Do you feel like healthcare is a basic human right?
I do, actually, especially being there. It's, you know, I feel like everyone deserves to have that met, the very basics. You know, if they would have had soap and a toothbrush and toothpaste, then they wouldn't, you know, have fungus infections or rotten teeth that are leading to even bigger problems with their body.
Education,
you know,
we try and give our kids
education,
now.
and that's the sad thing that they don't have there, is the education that we so easily can get here by going on WebMD. It's bigger than just medicine there. I always say, like, I don't want to go over there and change them to be more like us, you know, give them roads and malls and, you know, all that kind of stuff that we enjoy here, but just to give them just the basics.
So now that you've got some time to reflect on the experience, what do you think is important for the rest of society, our society, to know?
It doesn't take very much to help. Do you know what I mean? So if you know somebody who's making a trip overseas to do something, you know, it doesn't cost a lot to go down and buy some bars of soap or to buy some toothpaste or to just donate some money for the trip. And, you know, a lot of people were saying prior to leaving, like, you're not going to make that big of a difference in 5.5 days of being there, you know? And I was like, I'm not going to change the world in 5.5 days, but, you know, you change the world of some of those people that you saw. And a lot of the translators that we had there were like, you know, you don't know what this meant for us and for my village, because some of them were actually from the village of Oyugis. And for them, it was a big deal. For instance, we had different types of reading glasses, and we would have them come up and have a newspaper, and they would try on each pair of glasses to see what fit, and to see the looks on people's faces when they could read and see the letters in a clear way was just amazing.
Did this affect the way that you're going to look at nursing in the future?
It affects the way I look at a lot of things in life. It affected the way that I feel about things, you know, little things that I took like, oh, that's so serious, you know, I don't have this, or I don't have that, you know, and then you see these people living with such little. I learned a lot about simplicity and just enjoying what you have and where you're at, and not always having to like be greedy. We might be here giving them ibuprofen and Tylenol and, you know, giving them something little for them medically, but what they did for my spirit and my soul as a person and what they gave to me was far more than what I could give to the people there.
What a great life's lesson. Thank you so much for sharing that.
Yeah.
If you're really lucky, anybody can find a meteorite, but they're extremely rare. So we're fortunate enough to have a piece of this new Martian meteorite that fell in 2011 here at UNM. The key piece of evidence that these are from Mars comes from trapped atmospheric gases that are in the meteorites. It turns out that these gases are the same as the Martian atmosphere. And so when they're taken into the laboratory and heated up, the gas escapes. We measure the gas composition, and it's turned out that this is an exact dead ringer for the Martian atmosphere. The Martian atmosphere, of course, has been analyzed by NASA probes in the past. Any meteorite fall, for that matter, is highly desirable because It's a sample that's coming directly from outer space and hasn't been contaminated by the Earth's environment, hasn't been weathered. And so you know that what's in the sample is delivered straight from outer space. This is a fully fusion-crusted 68-gram piece of the Martian meteorite. And this is, of course, a fabulous specimen for display. But also, this is scientifically extremely valuable because it's completely encased in the fusion crust glass that formed as the meteorite fell through the Earth's atmosphere and was frictionally heated. For Mars, it's particularly interesting because Mars has the possibility of life, maybe in the past, possibly even the present. And so being able to look at a very fresh Martian rock is, with no Earth contamination, is really, really important to try to answer that question of whether there's life on Mars.
Thank you for watching. Do you have a question for our experts? Please email us your viewer questions and comments to askconnect@knme.org. Production support provided by the University of New Mexico.